Hello, everyone. We're going to try this doing the homework on here. So we're going to do chapter and do videos of this. Chapter 9. This is problem 5. Okay. And problem 5, it refers back to a seesaw that was shown in example 9.1. This example is in 9.2 section. And it says use a lot of the same things in the example, except for two changes. One of the changes is sort of baffling, and I'll explain why in a second. All right, so we're going to have here a teeter-totter like this. We're going to put our lighter child over here. The problem does change the lighter child's mass. We will do that in just a second. They do put the heavier child over here. This child's mass, according to the example, is 32 kilograms. This lighter child is now, let's see, was originally 1.6 meters. I think that stays the same. I'm taking a look really quick. Yes. So this lighter child, which now the problem states is now 12 kilograms. Originally it was 12 kilograms. And the distance between here and here is 1.6 meters. They also reference that the center of gravity of the board has shifted over. This is called the center of gravity. And I think I mentioned in class, hopefully I did. And if I didn't, the center of gravity means exactly that. All that weight can act at that center point. We can assume it's there for now. The biggest thing with center of gravity, this thing doesn't have mass. So we don't have to worry about it. I don't know why they mentioned it there, other than the fact that later on they do talk about more things. And so what they want to know is how far away does this have to be? How far away is this other person? So since we're rotating around this point right here, we can say, we first of all have to draw which direction is positive. For today, I'm going to do clockwise is positive. So the sum of the torques equals I alpha. That's our single formula that we're using. Now, the torques, first of all, what's alpha? It's not spinning, so this goes to 0. So if I look at this person here, their weight is going to pull it down this way. So this is M1G. This person's weight is going to be pulled down, so this is M2G. If I had the center of gravity, if there was a weight, a mass to this board, it would be here. We would call it M board G. But we don't, right here, I'm pointing, you can't see where I'm pointing, but this right here, that would normally be M board G. We don't have to worry about that because nothing's moving. I'm not nothing moving. It's a massless board. So M would go away. So I just have these two. So if I look at this side over here, if I look at the lighter child is going to want to move it in this direction. So if the lighter child is going to move it in that direction, it's my negative direction. So I got negative R F1 sine theta. Now F1, let's actually write down what F1 is. F1 is going to be just the force of gravity, M1G. Likewise, F2 is going to be equal to M2G. Now, over here on this side, I'll make it red for a second just to change up the color. This is what I want to rotate this way. That's where that person, the heavier child, is going to push it down. So therefore, I am going to get, for the heavier child, plus, because it's going the positive direction, so this should be R1, by the way, R2 F2 sine theta, technically this is 1 and 2, equals 0. Now, theta 1 and theta 2 are 90 degrees. They're 90. So if you think about it, if this is the direction, let me go back to my red. If this is the direction of the force from the heavier child, it's 90 degrees away from the board. Sine of 90 degrees goes to 1. And both of them are doing that. So you get rid of those. Going back to black. So if I look at the first formula, R1, so how far away is that person? That child is 1.6 meters away. Times F1, which would be M1G. Plus, and I forgot my negative sign there, plus R2. R2 is what we're solving for. We labeled it up here as X, so we're going to say X times F2, which is M2G, equals 0. Now I'm going to bring this chunk over to this side of the equation just to make my life a little easier. So I get X times, now M2 was 32. times 9.8 equals, and if I take that one negative 1.6, I got to add it to both sides. So I get 1.6 times M1, which in this case is 12, times G, which is 9.8. So I'm going to do the multiplication on this side. I'll bring up my handy dandy calculator because I should have just, oops, I could have done it that way. That's all right. So if I'm going to do the 32 times 9.8 first. So 32 times 9.8 gives me 313.6 times X. By the way, if you were trying to keep score, this technically is kilograms. This is meters per second squared. Likewise, kilograms, meters per second squared. Equals, so now I'm going to do this whole thing. So 1.6 times 12 times 9.8. And if I do that out, I get equals 188.16. So now I'm going to divide both sides by 313.6. 313.6. X comes out to be 0.60 meters. So if my teeter-totter is massless, I don't have to worry about the center of gravity, and therefore I can just treat it as we did the door problem in class. So when we did problem number 1 in class. Hopefully this clears up a lot of issues with number 5. Now, number 7, we're finally going to get into where we have our center of mass. Actually, no, they still don't have a mass. So let's just we'll do another one like this. So I need to add a page. So our next page we're doing number 7, same chapter. So 2 children of mass 20 kilogram and 30 kilogram are balanced on a seesaw, pivot located at the center of the seesaw. Okay. So if the pivot's located at the center of the seesaw, by default, we don't have to worry about the mass of the seesaw becoming an issue. Because the center of mass of the pivot would be right here. And if the center of mass is right in the middle where it's going to rotate, that doesn't make any difference. It doesn't rotate. It's sort of like if you have a pen you balance in the middle, if you press on that the balance point, you don't fall over. All right, so we have a 20 kilogram and a 30 kilogram. So the 20 kilogram has to be farther away. 20 kilograms. The 30 kilogram has got to be closer. 30 kilograms. And now the distance separated by a distance of 3 meters. Okay. Now this is going to be oh, by the way, back one step. I'm going to go back a page. Here, this was a level 1 problem. It was a level 2 in terms of being crappy explanation in the book, which I apologize. This one here is going to be a level 2 problem, maybe even a level 3. We'll see what happens. So I don't have these distances. If I was going to do the same thing as what I usually do, I need a distance here and I need a distance here. So we'll call this X1 and X2. I don't have either one of those. But I do know one thing. I know that X1 plus X2 is equal to 3 meters. Okay, so that's one equation I know. I also know the sum of the forces, not sum of forces, sum of the torques, not forces. I'm still stuck in previous things. The sum of the torques is equal to I alpha. So once again, I'm going to draw what forces are here. So I have M1G pulling down on that side. I have over here M2G pulling down this side. And for the fun of it, let's reverse it just to show you that we can do it the other way. That's going to be positive. Okay. We are not teetering nor tottering, so therefore our alpha is 0. We're not rotating. So we look at problem number 1. We know, okay, so this M1G, this here is going to be pulling downward. Downward will allow it to rotate in the same direction as our positive value. So therefore, I get here that I'm going to get X. So remember that torque, I'm going to write it up here, is equal to RF sine theta So I am going to r in this case is x1 times the force, which is m1g, and theta is going to be 90 degrees because once again we have this as 90 degrees, so sine of theta will go to 1. So that's in the positive direction. The other child will be pulling it in the opposite direction. So it'll be x2 m2g equals 0. All right. There's a problem still. I still have two unknowns, but I have two equations and two unknowns. Here's equation number 1. Here's equation number 2. So I'm going to take equation number 1 and solve for one of them. I'm going to solve for x1. Or yeah. Oh no, I'll solve for x2. x2 is equal to 3 minus x1. So that's just taking this equation and putting it here. And I'm going to take that and substitute it back into that equation. So I'll change color for the fun of it. So I will have then x1 m1g minus, now this whole thing has got to be put in there, so I'll get 3 minus x1 m2g equals 0. And now we have some fancier math that we have to worry about. So we'll have x1 m1g minus 3, so I'm going to bring this in here, minus 3 m2g plus x1 m2g equals 0. Because remember, this minus and a minus become a plus. That's where that gets there. So I'm going to take this, put it over here. I'm going to combine the other two terms. So I can factor the x1 out. So I have x1 times m1g, that is supposed to be a g each and every time, plus m2g equals 3 m2g. Now I'm going to go to a new page. We're going to continue this problem. As I hear a cat outside meowing. Say 7 continued. And so now what we need to do is we need to stick in our values. So let me go back a page just to grab them. So we have this x1 times m1g. Let me just rewrite the equation. x1 times m1g plus m2g equals 3 m2g. Let me just verify that. Yes. And now m1 is 20 and m2 is 30. So x1 is times 20g plus 30g. Oh, geez. Wait a minute. Back. Well, yeah, we'll go back. 20 times 9.8 plus 30 times 9.8 equals 3 times 30 times 9.8. x1 times, so let's solve that inner piece. So basically that's going to be 50 times 9.8. So we get 490 equals now 3 times 30, which is 90. And then we're going to multiply that by 9.8. We get 882. So x1 is equal to, we're going to divide 490, and so divided by 490, and we get the fact that Dr. Walters can't type into his calculator correctly. We get 1.8 meters. So that's part of the answer. So therefore, if I had that, we know that x1 plus x2 is equal to is equal to 3 meters. Get the eraser out. I have 1.8 meters plus x2 is equal to 3 meters. If I subtract 1.8 from both sides, x2 is equal to 1.2 meters. Now we'll double check. x2 is the heavier child. So you see it does place him closer than the lighter child at x1. x1's farther away. So does our answer make sense? Yes. Yay! Problem 7's done. All right, now we move all the way down to problem 20. And for problem 20, we will add a new sheet. When you need to raise a 250 kilogram mower a distance 6 centimeters above the ground, change its tire. If you had a 2-meter long lever, where would you place the fulcrum if your forces was limited to 300 newtons? Okay, so we want this. We'll put a lever here. We have a mower over here. Here's my mower. My mower is going to be here. We'll just make a block. We'll put a little handle on it, some wheels, and one of those little funky tops. Okay. My mower here says that it weighs 250 kilograms. And we want to raise it 6 inches. I have a 2-meter long lever. So we have 300 newtons of force that we can pull down from someplace else. So we'll just put 300 newtons here. There's my force pulling down. This is so I have it mg pulling down over here. What can we do with that? Well, once again, we can take a look at this. The 6 inches, if my lever is 6 inches, I don't have to worry about many other things. I can just put this here. This is 6 inches above. So therefore, if I lift this to be level, I'm all set. I'm 6 inches off the ground. So once again, sum of the torques equals I alpha. We're not spinning it, so it goes to 0. Here we have the distance. We'll call this x1. We'll call this distance x2. So we don't know where the fulcrum is, but we do know that x1 plus x2 equals, let's see, how long was our fulcrum? I mean, our bar, 2 meters. So if this is the case, we can now go write our equation. Let's make this direction positive just to keep flip-flopping back and forth, which means this will produce negative torque. This one will produce positive torque. We'll go back to blue now to give you a different color. And so we can now say for x1, it's going to be in negative direction. So we will get a negative x1 times 300 newtons, because that's the force. And the sine of theta will go to 0. And sine of theta would be 1 because we're at 90 degrees. All right, the other one will be in the positive direction. So we'll get x2 times 250 kilograms times g, which is 9.8, equals 0. Now, I'll stop here for a second. What about the 6 inches? Well, the way we're solving the problem, we don't have to worry about the 6 inches because we made this 6 inches tall. There are other ways to do this problem. There are some ways, if you looked it up in the book and found a different way to do it, I'm okay with that. I'm just showing you, just using the principles we learned in class, what could we do? So we have this chunk here. So once again, I have 2 equations, 2 unknowns. So let's solve this equation first. So we're going to do the same thing. We'll solve it for x1 this time. x1 equals 2 minus x2, and we're going to stick that back in here. So we have a negative 2 minus x2 times 300 plus x2 times 250 times 9.8 equals 0. All right, so we're going to distribute all this. We'll try to figure this out. So we're going to have a negative 600, right? Because the negative 2 times the 300. And we have a negative times this, which is positive. I forgot the 0. So it's plus 300 XL. XL, not XL. My goodness gracious, it's X2. Plus, now we have 250 times 9.8. 250 times 9.8 gives a value of 2450 equals 0. just checking my math here really quick. So I have this, that's going to be there. Must have made some error. 1 second, please. We can pause. Oh, they're doing mechanical advantage that way. Wait, did I do the wrong problem? No, I didn't. Okay. I somehow thought I did a different problem. Oh, let me see. I apologize, everyone, for the pause. Because this is not where I thought you were going. Well, I was going with it, so. Trying to. Where did I make the mistake? So we look at this here. We have this to the 2, right? So therefore I solve this. X1 will be 2 minus X2. So you get a positive X2 there. 250 kilograms, right? 250 kilogram more. And we have a net force. All right, so I have either a calculation error or I'm doing something, got something funky. All right, I'm going to come back to this in a different video because something's not coming out right on 20. Because what's going to happen, let me show you why first, because then you can understand where I'm coming from here. So if I do this out, I'm going to combine this and this for a second. So if I combine those two together, I'm going to get 2450 minus 600. And so basically I get 300 x2 plus 1850 equals 0. And so here's my problem with that. If I go ahead and solve this, I'll get 300 x2 is equal to a negative 1850, or x2 is equal to 1850. I got to put it here. X2 is equal to 1850 divided by 300. And I've screwed up my calculator. 1850 divided by 300. 6.16, but it's a negative 6.16, which means according to this, I would have to have this thing, my force would have to be 8 meters away for it to raise it that much, but we only have 2 meters long. Why do I say I have to have 8? Because if you put this negative 6.16 in here, x1 is at 8 meters away. So it's not 8 meters away. So we have a problem because you only have 2 meters to go, which means I made a mathematical error someplace and I can't find it right now. I will find it and repost a video for number 20 in a minute. I just made the mistake of I'm doing all these videos at once. I don't have good editing software. So we are going to sidestep for a second. I apologize. And maybe I'll just I could do that. So I could do that problem. So now we're going to go to chapter 10. Maybe I'll just do that one in class for sure, because I have time to look it up. All right, chapter 10, problem number 6. So problem number 6, suppose a piece of dust finds itself on a CD if the spin rate is 500 RPM. Now, I had somebody ask me about this. 500 RPM, what does that stand for? It means 500 revolutions per minute. And the piece of dust is 4.3 centimeters from the center. Okay. What is the total distance traveled by the dust in 3 minutes? Okay. So we want to know how far did the dust go. So what we could do is we could set up our little chart. Normally our original chart would be, I'm going to show you this straight up, X final, X initial, V final, V initial, A, and T. And remember though, we're able to go this direction and transform all these values into, well, actually those don't change, but to be theta final, theta initial, omega final, omega initial, alpha, and T stays T. T doesn't change. So we're going to go ahead and take some of these values out there. So we know that where did I put the problem? Number 6. There we go. So our omega would be this revolutions per second. So equals, well, actually initial 500 revolutions per minute. And we're going to have to convert that. We'll talk about converting that. So therefore, 1 revolution is 2 pi radians. And a minute, so I have 1 minute is 60 seconds. So if I do that whole thing out really quick, so I have 500 times 2 times 3.14 divided by 60. This ends up being 52.3 bar radians per second. Alpha is going to be equal to 0. And what they said was at a spin rate of. In other words, it's not changing. So we don't have to worry about that. Theta 0 can be 0. We can define that to be 0 if we want to. And what we can do is we can say this direction is positive. It doesn't make any difference because they're not asking us for the direction. It just says total distance. Remember, distance is basically the scalar piece. It'd be displacement if we were looking at a vector. So really what we want to do is find that. So we can go look at our traditional equations. Once again, the traditional equations be XF equals X initial plus V0T plus 1/2 AT squared. We also have V final equals V initial plus AT, and V final squared equals V initial squared plus 2A delta X. So if we were converting these into our equations of rotation, remember this would then be, how do I want to do it? I'll do it here. That's fine. This would be theta final equals theta initial plus omega naught T plus 1/2 alpha T squared. I'm going to stop right there for a second. I want theta final. I have theta initial. I have omega naught. I have T. Do I have T? Yes. 3 minutes. Oh, wait a minute. Jeepers. All right, I'll show you something neat. We know alpha. Alpha was 0 because they didn't expressly give us an alpha. So therefore, I could say theta final is equal to 0 plus, now omega naught and T. Now, we did all this conversion to radians per second, but they gave us the time in minutes. And we originally had revolutions per minute. So if you wanted to cheat, it's not really cheating. It's 500 revolutions per minute multiplied by 3 minutes. If you wanted to convert it to seconds, radians per second, it's 100% correct as well. This is one time we can leave it in this unit because it's the only unit we're dealing with. We're not dealing with anything else. So we'll get theta F in terms of revolutions. So theta F is equal to 1500 revolutions. Now, if you didn't want to do that, we have to convert this to seconds. So therefore, I will say it's times. So I have 60 seconds for every minute, which is equal to 180 seconds. So I would then take the answer, I'll circle in red, the 52.3 and multiply it by the 180, because that's what this would. So this would then be 52.3 radians per second. This is a 3 times 180 seconds. So this would get us in terms of radians. And the red answer, if I did that out, would be, let's see, 52.3 times 180. My thumb went across the screen and took away my answer. Times 180. I get 9,414 radians. Now, I'm going to do a quick conversion. Let's convert radians back to revolutions. There's 2 pi radians in every revolution. So therefore, I'm going to divide this by 2 pi. So divide by 2, divide by pi, and hopefully, and we do, we get 1,500 revolutions. So this answer here is the same as this answer here. It's just different because of the unit. Okay, this is why I said this chapter here, this chunk that we're doing, is exactly like what you did in the first chapter of the first thing we did, just with rotation. All right, let's do number 7. In number 7, a gyroscope slows from an initial rate of 32 radians per second. All right, so now we're going to go ahead. We're going to straight into our rotation stages. Theta final, theta initial, omega final, omega initial, alpha, and t. So it says a gyroscope slows from an initial rate of 32 radians per second. Initial rate, that's going to be a velocity, 32 radians per second, at a rate of 0.700 radians per second squared. That is going to be in acceleration, 0.0700 radians per second squared. Since we're slowing, this means it's a deceleration. We're going to put a negative there. And our initial value can be 0. We can always label that to be 0. Now, part A asks, how long does it take to come to rest? If I'm resting, my final omega has to be 0. And I don't care what my initial, how far I went, at least not yet. So if I have this, I can look at my equations and my big 3 equations. Let's see, I'll just write the 3 equations here. So I have theta F is equal to theta initial plus omega initial t plus 1/2 alpha t squared. I'm also going to have omega final is equal to omega initial plus alpha t. And lastly, I'm going to have omega final squared equals omega initial squared plus 2 alpha delta theta. All right, the first question was, how long does it take to come to rest? So we're trying to find this. I have the omegas, I have alpha, so this is 1, 2, and 3. Equation 2 is the logical choice for us. So equation 2 states omega F equals omega initial plus alpha t. I put in the values. 0 equals 32 radians per second. 32 radians per second, plus alpha, which is a negative 0.7. Well, I should put the radians per second squared just to keep us in track. Times time, which is what we're solving for. So I'm going to take this and move it over here. And so therefore I get 0.7 t is equal to 32. And then t is equal to, so 32 divided by 0.7, 45.7 seconds. Now, that's part A. Part B asks for how many revolutions does it take before stopping. So we're not going to solve for revolutions yet. We're going to stay in the radians space. So we have two different choices of what we want to use. Let's use, we'll use the first one just to make it, oh no, let's use the third one. We'll use equation number 3. So WF, so we're going to use WF squared equals W initial squared omega. It should be omega, not W. I apologize. I call it W sometimes in my head. Omega F squared is equal to omega initial squared plus alpha, plus 2 alpha. I was looking at the wrong formula. Give me that thing, please. 2 alpha theta final minus theta initial. All right, let's put our values in. So this is 0 squared is equal to omega initial squared, which was our 32 radians per second squared, plus 2 times alpha. Alpha was our negative 0.7 radians per second, times theta F. And by the way, theta 0 went to 0 because that's what we did that. I'm going to bring this over to here. And so I'm going to get 1.4 theta F is equal to, I just did the multiplication there, 32 squared. My handy dandy calculator tells me is 1024. So theta F is equal to, I'm going to divide both sides by 1.4. Theta F will be 1024 divided by 1.4. I get 72.86 radians. Now, we don't want radians. We need to convert that. So, crap, I got to use another page. That's okay. It's all electronic. So the 72.86 radians, I want that to be in rotations, right? Revolutions. So I'm going to call ReV for revolutions. So what do I have to do? Well, I know there's 2 pi radians for 1 revolution. And so if I take my 72 divided by 2 divided by pi, and I get here a sneeze. And that sneeze equals 11.6 revolutions. So because we're converting back and forth, this might be like a level 2 problem, or level 2-ish. Let me erase this. Come back. There we go. I say level 2-ish, then I put level 1. All right, that was number 7. Now we'll do number 12. And I still owe you 20. I will figure that out in a minute. Number 12 states the triceps in the muscle in the back of the upper arm extends the upper forearm. This muscle in a professional boxer exerts 2.00 times 10 to the third newtons of force with an effective perpendicular level arm of 3 centimeters, whose an angular acceleration, What is the moment of inertia? Wait, I gave you 12. Why did I give you 12? Oh, because you're able to solve. Okay. There's a lot of information here. So we know, so here's my puncher punching outward. And the puncher has a force 2.0 times 10 to the third newtons. Okay. So that's my force coming outward. Lever arm of 3 centimeters produces an angular acceleration. Now we know the angular acceleration is equal to 120 radians per second squared. And what I was asking you was for the moment of inertia. Remember how we said the sum of all the torques is equal to I alpha. We finally have an alpha. What we want to solve for is the I. So torque of our arm would be the force RF sine theta is equal to I alpha. Our force is this large force here. That is the force here. So we're going to stick that in. The R is our lever arm. So we'll say 3 centimeters. So 3 centimeters converted into meters would be 0.03 meters. So we have 0.03 meters times our force, which case is 2 times 10 to the third newtons, times the sine of 90. We'll get that. We'll put that in there. Equals I times alpha, which is 120 radians per second. I need to make that. This is all written correctly. I just need to shift it over. For those that are not watching the video, they won't know what the heck I just wrote. So I'm going to put that in there. So we're going to have here 0.03 times the force, which is 2 times 10 to the third. Oh, this should be meters. This is newtons times the sine of 90. I'll put it in there explicitly, equals I times alpha. And alpha is what we're measuring, which is 120 radians per second squared. So this goes to 1. So now we can have everything that we knew. Multiply 0.03 times 2,000. I should just put 1,000, but anyhow, or 20,000 to the third equals. So this here is going to be 6 is equal to I times 120. Divide both sides by 120. Actually 60. I mistyped. There we go. I thought that was too small. So now 60 divided by 120, I is equal to 0.5, 0.5. Now the units at I, let's say you didn't know what the units are. Since you know that this is radians per second squared, and this over here is meters, and this is kilogram meter per second. Anyhow, this is a weird unit. Kilogram meters squared is the unit. What I want you to see is that we can play with I, with an alpha and I, and solve for what I is. I'd probably give you the unit on a test because I didn't go over the unit on that as much. So I apologize for the unit issue. So other than problem 20, I hope I explained well what I was putting out there, and we can talk more about it in class. But that is it for now. I'll turn on my camera here. I left the camera off so it's easier to see stuff. So I hope you had a good time. Let me know if this works, because if it doesn't work, I don't want to do it again. But if it does work and it makes it easier, maybe even to go back and review things, let me know. And if you want them separated out so you don't have to watch one long video, you just want to watch the part about your question itself, let me know that too. Okay? Take care, and I will see you in class. Bye.